All right, let's jump into a deep dive, shall we? Today we are tackling diagrams and their role in philosophy.
Awesome.
We're working with excerpts from the Stanford Encyclopedia of Philosophy's entry on diagrams. And, well, let me just say it's a dense one.
Yeah. It's a really interesting entry.
There is so much to dig into.
Yeah.
We'll be looking at how diagrams have been used for logical reasoning, some of the limitations of visual thinking, and even how Euclid's geometry, that super foundational math stuff, wasn't immune to the quirks of diagrams. So get ready. It's going to be a wild ride.
Yeah, diagrams, I mean, they seem so simple, right? Like
Right.
such an intuitive way to represent information.
Yeah.
But when you start digging deeper, it gets surprisingly complicated.
Yeah.
And what's really fascinating is that even though diagrams are probably one of the oldest forms of communication, I mean, going way back in human history, formal logic has primarily focused on sentences.
Right. It's like we prioritized words and left pictures behind, even though we use them, all the time to understand things. And the article points out that recently there's been this surge of interest in diagrammatic reasoning, not just in philosophy, but across a ton of fields.
Yeah, it's really cool how much attention it's getting. And it makes sense. I mean, you've got philosophers of mind and cognitive scientists who are super interested in how diagrams relate to mental representation. Then you have all the logicians who are trying to figure out the formal rules and validity of diagrammatic systems. And then, of course, computer scientists are always looking for ways to implement diagrams in various applications, too.
Right. So it's this really cool intersection of different disciplines, all trying to figure out how these visual tools work.
Yeah.
And before we go too far, I think it's important to remember that we are mainly talking about external diagrams, like the ones we draw or create, not like the mental images we might form in our heads.
Right.
Those are obviously important too, but those are a whole other conversation.
Right. Exactly. Though, of course, mental imagery plays a role. Our focus today is on those systems of diagrammatic reasoning that have been formalized, especially within logic.
Okay, cool. So let's start with something everyone's probably seen at some point. Euler diagrams.
Yeah.
Using circles to represent logical relationships just seems so elegant,
Yeah.
so simple.
Euler's system is definitely elegant in its simplicity. He used circles to visually represent those four basic categorical propositions in logic. All A or B, no A or B, all that stuff.
Right.
And for those universal statements like all A or B, it's incredibly intuitive.
Oh, yeah.
You draw circle A completely inside circle B, and boom, you visually captured that relationship. No problem.
And no A or B is the two circles that don't overlap at all, right?
Yeah.
It's almost like a visual version of set theory.
Precisely. But this is where things get a bit tricky. Euler tried to extend the same spatial containment idea to those existential statements like some A or B. He'd show part of circle A overlapping with part of circle B.
But wouldn't that same diagram also work for some B are A?
Yeah.
And couldn't it even be interpreted as some A are not B? It seems like things start to get ambiguous really fast.
Yeah, you're absolutely right. You hit the nail on the head there. Euler's system is great for those universal statements, but those existential ones, they introduce a lot of ambiguity. To resolve this, you'd need a whole bunch of additional rules and conventions, which makes the whole system less visually clear.
Yeah.
So, yeah, it kind of loses its elegance.
So it's like Euler diagrams are great for a quick visual grasp of some basic logical relationships, but then they kind of fall apart when you try to get more complex, which I'm sure our listeners can relate to that feeling of, philosophical frustration when a seemingly simple system just breaks down.
Yeah, exactly. And that's where Venn diagrams come in. John Venn was very aware of these limitations of Euler's system, and he came up with a pretty clever solution. Instead of trying to represent those existential claims directly with spatial relationships, he focused on creating what he called primary diagrams.
Primary diagrams, what are those exactly?
Okay, imagine two overlapping circles, but there's no shading or markings inside them.
Okay.
So in Venn's system, this doesn't actually tell you anything specific about whether there are any A's, any B's, or if they even overlap at all.
Okay.
It's just representing all those possible relationships without committing to whether any of those possibilities are actually true.
That's clever.
Yeah.
He sidesteps that whole ambiguity issue by not making any existential claims at the outset. But how did he handle those universal statements like all A or B? It seems like Euler's, visually intuitive approach of containment is out the window here.
Right, exactly. So Venn introduced the idea of using shading to represent those universal statements. So to say all A or B, you'd shade the part of circle A that's outside of circle B. This basically means that everything in A has to also be in B.
Okay, so to represent no A or B, you'd shade the entire overlapping section of the two circles, right?
Yeah.
And then if you combine all A or B and no A or B, you end up with the entire circle A shaded, which would mean nothing is A. That makes sense, even if it's, a bit less visually obvious at first glance than just having that one circle inside the other one.
Right, yeah. Venn sacrificed some of that immediate visual clarity to gain greater flexibility and precision with his system. But surprisingly, he didn't really address how to represent those existential statements that caused so much trouble for Euler.
Of course, leave it to Charles Peirce to come along and try to, fill in those gaps.
Right. Always got to take things a step further.
Mm-hmm.
So Peirce took Venn's system and he extended it. He replaced Venn's shading with a symbol O to mark a region as empty. Then he added an X symbol to indicate that something actually exists in a particular region. And then if you needed to represent a disjunction, like either this region is empty or something exists here, he would connect those symbols with a line.
So Peirce's system could finally handle something like all A or B or some A or not B all in one diagram.
Yeah, all in one.
But it definitely seems like things are getting visually complex, like a lot more going on.
Right, yeah, for sure. There's definitely a trade-off there.
Yeah.
More expressive power often comes at the cost of visual simplicity. But, Peirce's crucial insight, I think, was that diagrams can have their own set of rules for manipulation, just like you have in algebra. So you can transform diagrams according to those rules. There are correct and incorrect moves, just like in a game.
Hold on. So you're saying we can, manipulate diagrams according to specific rules? Like, it's not just about looking at a static picture. There's this whole process of transformation involved.
Precisely. And this was a huge step towards formalizing diagrammatic reasoning. Now, Peirce, he didn't have the tools to fully prove the correctness of his rules, but he laid the groundwork for later logicians to come along and really build on his ideas.
I bet somebody picked up that torch and ran with it, right?
Oh, you bet. Sun Jo-shin, building on Peirce's work, she actually developed two formal systems for these kinds of diagrams, Venn-A-Venn and Venn-7. And Venn-the-Sec is particularly important because it's been proven to have the same expressive power as a system called monadic predicate logic.
Monadic predicate logic.
Monadic predicate logic. That sounds a little intimidating.
Yeah, it's a bit of a mouthful.
Yeah.
But don't worry, we don't need to get into the technical details right now. The key takeaway is that monadic predicate logic is a well-established formal system for representing and reasoning about logical relationships. And the fact that Venn the second is equivalent to it means that diagrams, when formalized properly, can be just as rigorous and powerful as symbolic logic.
Whoa, okay, so that completely changes my perspective on diagrams. I always thought of them as more of a visual aid, oh, here's a helpful picture to go along with the real logic, which is done with symbols.
Right.
But you're saying they can actually be serious logical tools in their own right? That's right. Shin's work was groundbreaking because she actually proved that Venn the second is sound and complete. So sound means that any conclusion you derive using the system's rules is guaranteed to be valid.
Okay.
And complete means that any valid conclusion that can be expressed in the system can also be derived using those rules.
So it's not just some informal way of sketching out ideas. It's a system that can be used for rigorous deductive reasoning.
Exactly. And this really challenged a long-held assumption in logic that only symbolic systems could achieve that level of rigor. It's like diagrams got their street cred,
Oh, okay. My mind is officially blown.
Right.
Diagrams is a formal system of logic. Who would have thought? But I have a feeling this is just the beginning of our journey. We've talked about the power of diagrams, but I'm guessing there are also some limitations, some potential pitfalls, right?
You are absolutely right. As with any powerful tool, we need to understand not just the strengths, but also the limitations. And that's what we'll be exploring in the next part of our deep dive. Get ready to uncover the surprising ways in which our, visual intuitions can sometimes lead us astray.
Uh-oh. Sounds a little dangerous.
A little bit, but that's what makes it fun, right?
Okay. All right, I'm ready. Let's do it.
Welcome back to our diagram deep dive. So last time we saw how diagrams can be super powerful for logical reasoning. They can even reach the same level of rigor as symbolic logic, which is pretty amazing. But now we got to look at their limitations. And those limitations, well, they're often tied to that very thing that makes diagrams so appealing in the first place,
Mhm.
their visual spatial nature.
That's interesting. So the very thing that makes them so intuitive can also be their downfall.
Yeah, kinda. It's like our brains are so used to dealing with spatial relationships out in the real world, right?
Right.
That we might unconsciously carry over those assumptions into, more abstract reasoning. And this can lead to what logicians call representational inadequacy, which is a fancy way of saying that the spatial constraints of the diagram don't quite line up with the logical constraints of the system you're actually trying to depict.
Okay. I can see how that could be a problem. Could you maybe give us an example to illustrate this?
Yeah, for sure.
Yeah.
Let's go back to those simple Euler circles. Remember how we can use them to represent statements like sum A or B?
Uh-huh.
Okay, so imagine you've got four sets, A, B, C, and D.
Okay.
And you're given these premises. A intersects with B and C, B intersects with C and D, and C intersects with D and A.
Okay, I'm picturing those overlapping circles in my head. It's getting a little crowded in there.
Yeah, right. Lots of overlapping. So here's the catch. If you try to draw an Euler diagram that satisfies all three of those premises, you'll find that you are forced to create a region where all four circles overlap.
Mhm.
In other words, the diagram's going to make it seem like there has to be something that belongs to all four sets. A, B, C, and D.
So the diagram is visually implying something that isn't actually stated in the premises.
Exactly. The premises themselves, they don't require all four sets to have a common element. It's the spatial constraints of the diagram that are forcing this conclusion on us.
Wow, that's subtle. So even with something as simple as like overlapping circles, we can be tricked into seeing relationships that aren't logically necessary.
Yeah, it's pretty sneaky. And this problem is actually related to a mathematical theorem called Helly's theorem, which comes from convex topology. It basically says that if you have a bunch of convex shapes and every three of them have a point in common, then all of them have to have a point in common. But that kind of spatial necessity, it doesn't always carry over to logic.
Right, like the diagram is imposing this rule on us that doesn't actually apply to the situation we're reasoning about.
Exactly. And this constraint hypothesis, as it's sometimes called, it's not limited to Euler circles. It can happen with any diagrammatic system where the spatial relationships that are like built into the system might mismatch with the logical relationships you're trying to represent.
Okay, so diagrams can be misleading, even if they look perfectly clear and intuitive. This makes me wonder about the whole idea of diagrams being more effective than, symbolic logic.
Hmm.
If they can lead to wrong conclusions, shouldn't we just stick with sentences and formulas?
That's a really good question, and it gets to the heart of what we actually mean by efficacy when we talk about diagrams. While diagrams might have psychological benefits, like they can make information easier to grasp or help us see patterns, they don't automatically guarantee logical correctness.
Right, just because something is easy to understand doesn't mean it's actually true.
Exactly. And it's important to remember that many diagrammatic systems, unlike most formal systems in symbolic logic, are incomplete. This means they can't represent all the logically possible situations. And they can also be incorrect, as we saw with that Euler circle example.
So it's not like a simple case of diagrams are better or symbolic logic is better. It depends on what you're trying to do and what system you're actually using.
Right. Each has its strengths and weaknesses. But there's another intriguing aspect to this whole issue of diagrams and their potential for error. Some diagrammatic systems, just by their very nature, can't even represent contradictions.
Now that you mention it, I can't really picture a diagram that represents something like A and not A. It's like a visual impossibility.
Exactly. And this inability to depict contradictions might actually tell us something important about the nature of pictorial representation itself. It connects to Wittgenstein's picture theory of language, which holds that a picture can only depict a possible state of affairs.
Oy.
Since a contradiction is by definition not a possible state of affairs, it can't be pictured.
That's a fascinating connection. So the limitations of diagrams, when we really examine them, can actually deepen our philosophical understanding of representation itself.
Yeah, pretty cool.
But let's bring this back to something a bit more concrete, shall we? What about diagrams in geometry, especially in, Euclid's Elements? I mean, geometry just seems like, the quintessential domain of diagrams.
You're absolutely right. Euclid's Elements is full of diagrams, and they seem to play a crucial role in his proofs. But even there, the role of diagrams has been a source of debate among mathematicians and philosophers.
Yeah, I can see how that would be tricky. On the one hand, Euclid's proofs seem to rely so heavily on diagrams, but on the other hand, there's this traditional view that diagrams are just illustrations, and that their use in a proof actually points to a lack of rigor.
That's the classic dilemma. But a philosopher of mathematics named Ken Manders, he challenged this traditional view in a really insightful way.
Oh,
He argued that Euclid used diagrams in a very specific and controlled manner, and that their use doesn't necessarily undermine the rigor of those proofs.
okay, I'm intrigued.
Yeah.
So how did Manders reconcile the visual and the logical in Euclid's work?
Well, Manders' key insight was to distinguish between two types of properties that we can see in a diagram: exact and coexact properties. So coexact properties are those that remain the same even if you make small changes to the diagram. Think about the topological structure, like containment, and the arrangement of parts.
Okay.
Exact properties, on the other hand, are those that are super specific and sensitive to even tiny changes, like the precise length of a line or the measure of an angle.
So if I draw a triangle, the fact that it has 3 sides and 3 angles, that would be a coexact property. But if I measure those angles with a protractor and get specific numbers, those would be exact properties.
Exactly. And what Manders observed is that Euclid, in his proofs, he only ever draws conclusions about coexact properties from the diagrams. He never uses those diagrams to infer anything about exact properties.
That's clever. It's like Euclid understood that relying too much on the specific details of a diagram could be dangerous. Like, those details might not hold true in all cases. So by sticking to those more general topological features, he avoided making those assumptions.
Precisely. But there's still a potential problem when it comes to constructions in Euclidean proofs. So, adding a new element to a diagram, like drawing a line or a circle, that can sometimes make the diagram unrepresentative of the general case that you're actually trying to prove something about.
Okay, I think I see where you're going with this. Can you give us an example?
Yeah, sure. Imagine you're starting with a diagram of an acute triangle,
Okay.
and you want to prove something about perpendiculars. So you construct a perpendicular from one vertex to the opposite side. In this case, the perpendicular will fall inside the triangle.
But what if you were dealing with an obtuse triangle? Wouldn't the perpendicular fall outside the triangle?
Exactly. Your initial diagram, it might have led you to believe that the perpendicular always falls inside the triangle, but that's not true in general.
Right.
The construction itself can actually alter the representational scope of the diagram.
So how do you, account for this problem of constructions potentially changing the meaning of the diagram?
Well, there are a couple of formal systems that have been developed to address this challenge. They're called FG and U, and they offer different but equally fascinating approaches.
Okay, lay it on me. What are the key ideas behind these systems?
So FG takes kind of a head-on approach. It says, look, if a construction can result in multiple cases, let's just generate all those cases and see what coexact features remain true across all of them.
So it's like a brute force method of making sure your conclusions are general enough to cover all the possibilities.
Exactly. It's systematic and thorough. But the question is, how do you actually generate all those possible cases, especially
Right.
with complex constructions?
Right.
Well, that's where the ingenuity of FG comes in. It defines lines and circles in a purely topological way, making them super flexible. This flexibility allows for a really systematic way to generate all those possible cases, a method that can actually be implemented in a computer program.
So FG is all about realizing possibilities, exploring that full range of what a construction can actually produce. What about U? Does it take a different approach?
Yeah, U is a bit more subtle. It allows diagrams to contain partial information from the start. So when you add a construction, the diagram doesn't immediately reveal all the relevant relationships. You have to derive those relationships using the system's rules.
So it's less about generating all possible cases and more about carefully deriving the relationships that actually follow from a construction.
Exactly. And this reflects a deeper kind of philosophical distinction between how FG and U view the role of diagrams. So FG sees diagrams as realizing possibilities, while U sees them as representing complex situations.
That's a fascinating distinction. It seems like both approaches have their own strengths and limitations. But what's clear is that diagrams in geometry, even in something as seemingly straightforward as Euclid's Elements, are way more nuanced and complex than we might initially think.
Absolutely. The relationship between visual intuition and rigorous deduction in geometry, it's a fascinating area of ongoing research. And this exploration isn't just limited to geometry alone. We see diagrammatic systems being used in logic teaching, automated reasoning, computer science, physics, you name it.
It's like we're rediscovering the power of visual thinking and finding all these new and exciting ways to use it. But there's one piece of the puzzle we haven't really addressed yet. The connection between diagrams and the way we think, our mental representations. Do we actually think in pictures? Join us next time as we venture into the mind and tackle this age-old question. Welcome back to our diagram deep dive. We've gone deep on the logic, we've seen the pitfalls, we've even touched on how they work in Euclid. But now let's get into the mind. Do we actually think in pictures? It's a question as old as philosophy itself, right?
Oh, absolutely. It gets right to the core of how we represent the world in our minds. It's a slippery topic for sure. I mean, how do you even study something as elusive as mental imagery?
Right. It's not like we can just look inside and see what's going on, like, oh, there's a picture of a cat.
Exactly. Early psychologists, they relied a lot on introspection, just asking people to describe their inner experiences. But then, with the rise of behaviorism, mental imagery became like almost taboo in psychology. Too subjective, too unreliable for scientific study.
Really? That seems a bit extreme. I mean, surely we can't just ignore the fact that people do experience mental images, right?
You'd think so, wouldn't you? Thankfully, things started to change in the 1960s. Mental imagery made a comeback as a legitimate research topic, but this time researchers were a lot more cautious. They knew introspection had its limits, so they focused on designing experiments that could actually reveal the consequences of mental imagery, through observable behavior.
So instead of just asking people what they're imagining, they started looking for ways to measure its effects, right? Like, how does having a mental image actually change how people behave?
Exactly. And this shift in approach led to what's known as the imagery debate in cognitive science. On one side, you've got the pictorialists. They argue that at least some of our mental images are genuinely picture-like, that they share important properties with actual pictures.
So they're saying that, like, when I imagine a beach, there's something in my mind that actually resembles a photo of a beach.
That's the basic idea, yeah. And they have some pretty compelling evidence, too. For example, there are these studies that have shown it takes people longer to mentally scan across a large imagined object compared to a smaller one, just like it would if they were actually looking at a real picture. Makes you wonder, huh?
It does. But I'm guessing there's another side to this debate. Like, not everyone agrees with this whole picture in the mind idea.
Oh, right, you are. On the other side, you've got the descriptionalists, and they argue that mental images are actually more like descriptions. They're built from propositions or language-like representations.
So instead of a picture of a beach, my brain is holding onto this description that's like sand, waves, seagulls.
Well, yeah, you got the gist of it, though those descriptions can get a lot more complex than that. The point is, descriptionalists argue that all the experimental evidence for mental imagery can actually be explained without needing to bring in these picture-like representations. They say even when we're imagining, we're still drawing on our knowledge and understanding of the world, and that's, fundamentally conceptual, often rooted in language.
So it's a bit like the nature versus nurture debate, but for mental imagery. Like, is it more about the inherent structure of the mind, or is it shaped by our experiences and the language we use?
I like that analogy. It kind of captures the tension there. And the debate's still raging on. Both sides are coming up with ever more sophisticated arguments and experimental findings. It's a fascinating area of research, and one that's, closely connected to these big philosophical questions about how we represent the world.
It seems like we've still got so much to learn about the mind. But even if we put this whole picture in the mind debate aside for now, there's still that question of how diagrams, as these external things we create, can actually influence how we think.
For sure. Even if we don't have literal pictures in our heads, diagrams can still be really helpful for thinking and problem solving. They can actually change the way we approach a problem, what information we pay attention to, what kinds of inferences we can make. It's like they're shaping our thought process from the outside.
So diagrams as these cognitive tools, what kind of research has been done in this area?
One really key area has been comparing diagrams to sentences. Researchers are trying to understand how those two forms of representation differ computationally.
Computationally, you mean like how efficient they are at certain tasks?
Yeah.
Or what kinds of inferences they make easier?
Exactly. And there was this classic study done by Larkin and Simon that really showed how powerful diagrams can be. They found that people could often just read off inferences from a diagram much faster than they could derive them from a bunch of sentences, like way faster, even though logically those sentences were saying the same thing.
Really? So sometimes a picture really is worth 1,000 words. But why are diagrams sometimes so much more efficient? What's the explanation for that?
Researchers have come up with a few ideas. One is that diagrams tap into those spatial processing abilities of our visual system. They let us process information in parallel rather than one step at a time like we often do with language.
It's like our brains are wired to deal with visual information in a different way.
Right. And another idea is that diagrams can make implicit relationships explicit, which kind of reduces the mental effort needed to make those inferences.
It's almost like the diagram is doing some of the thinking for us, giving us a shortcut.
That's a great way to put it. And this idea of diagrams providing this free ride for our cognitive processes has been a huge focus of research. Researchers are really trying to pinpoint when and why diagrams offer this cognitive boost and, what the mechanisms are behind it. It's fascinating stuff.
It is. Makes you wonder if we should be using them a lot more, like in education, if they can help us think and problem solve more effectively.
Yeah, I think there's a huge potential there. And there's definitely a movement growing to incorporate visual thinking and diagrammatic reasoning more into education and training programs.
It feels like we're just scratching the surface, really. Like there's so much more to discover about how diagrams can help us learn and understand the world.
I totally agree. The study of diagrams is a really exciting field. It brings together so many different disciplines like philosophy, psychology, logic, computer science, even education. It's an area that's just bursting with possibilities.
Right. Well, that wraps up our deep dives into the fascinating world of diagrams. We've seen how they can be powerful tools for reasoning, how they can shed light on complex ideas, and even how they might connect to the way we think.
We've seen their strengths, their weaknesses, and their potential to both clarify and mislead.
I think it's safe to say that diagrams are a lot more complex than we might have initially thought. They're more than just pretty pictures. They're tools for thinking. And I, for one, am going to be looking at them with a whole new level of appreciation.
Same here. And I think understanding how diagrams work, both their power and their limits, can actually help us to be better thinkers in all areas of our lives, whether we're trying to solve a problem, understand a new concept, or just communicate more effectively. So next time you see a diagram, don't just glance over it. Take a moment to really appreciate the interplay of visual and logical thinking that it embodies. You might be surprised by what you discover.
That's a great takeaway. Big thanks to you for joining us on this deep dive into diagrams. And to our listeners, thank you for tuning in. We'll catch you on our next deep dive adventure.